Let's look at resonance effects on acidity. Now, we've had a video on this before, or at least some, but it bears looking at that again just so we can remember it. So, recall that for phenol, we had some resonance structures, and I'm just going to draw one to illustrate what I'm talking about. So there's one of the resonance structures, but we can also draw resonance structures where the negative charge is down here and the negative charge is over there. So there are some more structures, 4 total. By spreading out the charge, that makes this more acidic. Let's look at another species that we like to use, the carboxylic acid. Carboxylic acids have an additional resonance structure. Where we can put the negative charge on the other atom, the other oxygen atom. And then we have this hybrid. Let's compare that to an alkoxide, which just has one oxygen atom on it. This does not have resonance structures, therefore it is less stable. And so this, the conjugate acid of this, ethanol, is a lot less acidic than a carboxylic acid or a phenol. Let's look at some more examples here. Now, if you remember, by thinking back to acetone, and these protons right here, I'll draw one in. These protons have a pKa of about 20. So they're relatively hard to pull off. These protons, which are also alpha protons, they're right next to a carbonyl, actually they're next to 2, are a lot more acidic at 8.9 pKa. It's very easy to pull off these protons. You can do it with regular kind of bases like an NaOH. You could just take that right off. Let's draw some resonance structures to explain why. Actually, I'm going to draw this one over here. This first one. So we've deprotonated in one position there. Now, it's possible to transition this either to the left or to the right and form a double bond in between here. So I'm going to draw that going into there and that coming up there. So now I'll draw this structure over here. I could instead move the electrons over here to the other side. and get an additional resonance structure. So I have 3 resonance structures, and they move the negative charge. They're sharing it between these 2 oxygens, which are electronegative, and this carbon. Now, if we were to try to deprotonate one of the hydrogens over here, which in this case would not happen, but let's see what would happen anyway. So we've taken one of the protons off of this first carbon. We can draw resonance structures of that. And that's it. We can't draw any additional resonance structures. Now, it might look like we could, but remember, when we're drawing resonance structures, we cannot move atoms. And one of the things that I didn't draw in because I was using line structures is these 2 hydrogens. So we cannot remove those hydrogens just by drawing a resonance structure. So it's not possible to move this charge over to the other oxygen. So that's one of the reasons why this is significantly less acidic in this position, and why when we have it in between these 2 carbonyls, it's much more acidic because we can share the negative charge over more than one oxygen. Now, that's what happens when we have a negative charge. But let's look at what would happen if we have protonated something. So did you know that it is possible to protonate a carboxylic acid? So we can protonate acetic acid, especially if we just put some sulfuric acid in there, or something even stronger than sulfuric acid. But this has a resonance structure. And so if I were to move these electrons in between this carbon and oxygen and move those up, so I'm not making carbon with 5 bonds here, then I have this structure, which is a resonance structure because I haven't moved any of the atoms. I've just moved electrons. So this allows us to share that positive charge over 2 oxygens. So this is a little bit more stable. Let's contrast that with a protonated acetone. So this structure looks kind of analogous to our acetic acid. I've still just protonated a carbonyl. But the major difference here is there are no resonance structures. So this is less stable. Simply because we've concentrated that positive charge on just one oxygen, whereas here we can share it between the 2. Since this is shared, it's more stable. That makes this less acidic. This is less stable, so it's more acidic. Put another way, it would be easier to protonate this carboxylic acid in this way than it would be to protonate the carbonyl without any additional stability. So in order to form this, and I think we can, we would need a much stronger acid in order to accomplish this in any reasonable amount. Whereas up here, we can accomplish this with a lot less strong of an acid. Up here, we could look at this and say, well, in order to deprotonate this alpha hydrogen, we'll need a much stronger base than we will to deprotonate one of these alpha hydrogens because of the stability. So often we're looking at these things in a little bit of a backwards way. We look at what we're making or what we've started with to see how easy or difficult it would be in order to achieve that. And sometimes we need to do that just so that we can examine the resonance capabilities. If we can have resonance, then that will lead to a more stable ion. And more stable ions will then translate into either easier to remove protons because the anion is more stable, or easier to place hydrogens because it's more stable to move that positive charge around. So, thank you for joining me for this video, and we'll see you in the next one.